Go.
Hello, my dear students. I'm sorry I'm still a little hoarse and may have to harumph and cough through this a little bit. If it gets too bad, I'll take a drink of my tea or get a cough drop. But I want to quickly do our next video help session for exercise 2.3. Again, I want to go over those questions because there's a lot to do here. Basically, we're taking our elements now and we're combining them together to make compounds. And there's two kinds of compounds, ionic compounds, where we add together ions, charged forms of the atoms, of the elements, and molecular compounds that are covalent compounds, covalently bonded together instead of ionically bonded together. Ionic bonds are formed by the transfer of electrons. Covalent bonds are formed by the sharing of electrons. And we'll talk more about this when we talk about bonding and bonding energies. So I want to answer a few questions. These are wonderful test questions, although they would have to be changed into a more objective multiple choice format in the test I envision posting very soon, later this week. Which contains fewer electrons than the neutral atom? The corresponding cation or the anion? Remember, the cation is positively charged, the anion is negatively charged. It says which one has fewer electrons? Well, this is where I lose a lot of students, because when you gain an electron, you get more negative because the electron's negatively charged. And when you lose the negative electron, you get more positive. So even though you're losing something, you get more positive. Look at it as a metaphor for life. If you lose the negatives, the bad habits, the negative people around you, the negative things in your life, you become more positive. And it's the same with elements. So you might say it's elemental or it's elementary. Now, so which contains fewer electrons? The cation. Calcium at +2, the calcium cation lost 2 electrons. So it has 2 fewer than regular calcium. Number 2. So again, I'm going to read these off and answer them. I'm going to write some of them down, but not all of them. So you're going to have to follow along. Feel free to pause and rewind. But for now, I'm going to go over these questions, basically give you the answer. Okay? But remember the process. So these are important general concepts here, and then we're going to get into some specifics of either naming the compound given the formula or writing the formula given the name of the compound, with rules for ionic and covalent compounds. And don't expect exactly the same thing on the test, but I'll show you a few hints for how to quickly get through these. Now, what's the difference between an organic compound and inorganic compound? Organic compounds, organic means life or living, and organic compounds are the ones we typically associate with living systems, and they contain carbon and hydrogen. Okay? I know, like carbon dioxide in the air, most of which came from living organisms, it's technically an inorganic compound, but it doesn't have any hydrogen in it. But when you say organic chemistry, they're talking carbon chemistry. Okay, so things made of carbon are organic. What's the advantage of writing a structural formula as a condensed formula? And I'll do it, for example, for acetic acid, which has this structural formula: CH3C double bond O OH. And this H is the H that comes out, the H that we talk about when we talk about pH, that makes this an acid. And that's its structure. But its formula would be what? 1, 2, 3, 4 hydrogens, 2 carbons, and 2 oxygens. That's a chemical formula. I can also write this way. CH3, because this tends to stay together. COOH. This tells me the chemical formula doesn't tell me anything. The structural formula, structural model, tells me how the atoms are connected and who's connected to who. And the condensed structural formula still gives me some idea of how these are arranged. So the advantage is it's faster, shorter, easier to format. This would be impossible. You'd have to go to a JPEG or a PIC to write this, whereas this I can write with text, okay? So, lots of advantages. The majority of elements that exist as diatomic molecules are found in one group, and that is group 7A, the halogens. Okay? Chlorine, fluorine, bromine, iodine, astatine, all of those compounds are diatomic. So when I have chlorine, it's group 7, it has 7 electrons, and it wants to have 8. And chlorine. Each one of these has 7 electrons, and the way this works is these go with this one, and these 7 with the other. Each of them has 7. Instead of doing a transfer or something, they say, look, I have 7. Let me get that C and L more clear. You have 7. If we share a pair of electrons, we'll each have 8. And they form a bond. So in nature, chlorine is found as a gas, Cl2. Okay. And that's why. More information than you needed. Group 7A is your answer. It says, discuss the difference between covalent and ionic compounds with regard to the forces that hold them together. Covalent compounds are held together by covalent bonds. Ionic compounds are held together by ionic bonds. For example, when I make not Cl2, but NaCl, this is an ionic compound because I had a negatively charged chlorine combined with a positive charged sodium. Opposites attract to form the ionic compound sodium chloride. So, A, the force holds them together. Covalent bonds for covalent compounds, ionic bonds for ionic compounds. The melting points. Ionic compounds have much, much higher melting points. Okay? I want to say 800 degrees Celsius for sodium chloride, and incredibly hot. You couldn't melt it in your home unless you had very specialized ovens and equipment. Covalent compounds tend to have much lower melting points, to the point where at room temperature many of them are liquid or gases. What are the physical states at room temperature and pressure? Well, that kind of relates to the melting point, doesn't it? At STP, standard temperature and pressures, covalent compounds, we see more liquids and gases. Can't think of any ionic liquids, for example. And ionic compounds tend to be more solid. Okay? So, let's go on to the next page. And 1, 2, 3, 4, 5. There we go. 6. Classify each compound as ionic or covalent. So the first one is zinc phosphate. It's ionic. How do I know? Because it's a metal and a nonmetal. That's a salt. Anytime I combine a metal with a nonmetal, that is a salt. It's not salt, table salt. It's a salt. And phosphate is an ion that's listed in your table of polyatomic ions. There's one in your book. There's one in the chapters I've linked to on the Chem Libre website, and I will post just a copy of my favorite chart of the most common ions, including polyatomic ions like phosphate. The next one is an ionic compound. There's no metals. That's all nonmetals. And in fact, that looks like benzoic acid. The next one is potassium dichromate. That's an ionic compound because that Cr2O7 2- is in your chart of the polyatomic ions. And you know what? If you don't know these, either their names or whether or not they're ionic or organic, and you're working these problems, just Google it. Just type that into the Google search bar and it'll come back and tell you about this compound. The next one is I want to say it's, I forgot the name of it. It's a ethanol derivative, but with a sulfhydryl instead of a hydroxy group. And that is entirely a covalent compound. I want to say beta mercaptoethanol. Is that what it's called? Anyway, the next, and it's a covalent compound. E is NH4Br, ammonium bromide. That's an ionic compound combined with the ammonium ion and the bromide ion. Remember, the bromine, when it gains an electron and becomes Br minus, we change the name to ide, bromide. And the last one is dichloro-difluoromethane. It's actually a refrigerant. It's a covalent compound. Nothing ionic there. It's kind of hard to tell these apart. Just practice a little bit. And the next one says which are organic and which are inorganic. So the first one is, let's see, propanoic acid is what it looks like. And it is ionic because it's an acid. You wouldn't know that one. That's actually kind of a hard one that we're not ready for yet, but you should be able to know that it is an organic compound because of all the carbons and hydrogens. The next one is calcium chloride. Okay, that's ionic and it's inorganic. No carbon in there. The next one is yttrium nitrate. Shoo, these are some odd compounds. That's inorganic and that's ionic. D is H2S, hydrogen sulfide. It is covalent, although it's arguable, and it's inorganic, no carbon. That's the smell of Fort Worth, by the way. And the next one is sodium acetate. It's ionic. It's this compound that has separated into, if I may use this abbreviation, CH3COO minus plus H plus. Okay, so this H is the acid in our acetic acid. You know it as vinegar. Okay, this acid has a negative charge. If you combine it with sodium, the ic acid becomes the 8 salt, so we change its name to acetate. This is now sodium acetate. That's that 7E, and it's ionic and it's organic because it's got carbons and hydrogen in it. Now, this says numerical problems, but it's helping you by giving you all the numbers you need. Magnesium sulfate. You can go to Walmart and buy it. It's commonly used in medical settings to prevent shock when somebody's blood pressure drops and everything. Hang a unit of mag sulfate. They should say magnesium sulfate, but it's MgSO4. Okay, so let me start this. This is number 1, numerical problems. MgSO4. Okay, that's A. B is ethylene glycol. It says it has 6 hydrogen atoms, 2 carbon atoms, and 2 oxygen atoms. Oh, let me go back to that. Magnesium sulfate. So the magnesium, we write the cation first, Mg2+, and sulfate, SO4 2- from our table of polyatomic ions. Okay? And I will let you have that table when you take your test. And when you take this first test, it's going to be online. It's just, can you work through this? You just open up another window and Google it, okay? So, although it would be handier and faster to have the table of the polyatomic ions and the common ions in front of you, and a periodic table handy. So, the next one is ethylene glycol antifreeze. It has 6 hydrogens, 2 carbons. We usually do the carbon first, and then the hydrogen next, or you can do the oxygen next. Just depends on the functional group. So 4 hydrogen atoms and 2 oxygens. So it's C2H4O2. See how these work? Acetic acid is right there, which has 2 oxygen atoms, 2 carbon atoms, and 4 hydrogen atoms. But we always write the carbon first. If you wrote C2O2H4, nobody would say anything. But C2H4O2 is acetic acid. Potassium chlorate is D. So this was your C. So potassium chloride. Potassium is K. If you look at the chlorate, it's 1 minus, and it's ClO3, and that's potassium chloride. K is the symbol for potassium. E, sodium hypochlorite pentahydrate. That's a solid form, basically, of bleach, Clorox bleach. So it's something we haven't studied yet because we're lacking a lab, but you might think it says it has 1 chlorine, 1 sodium, 6 oxygen, and 10 hydrogen. But 10 of those hydrogens and 5 of those oxygens go with the pentahydrate. So it's sodium hypochlorite, ClO. You can look up the hypochlorite, -1 in the table. And then for hydrates, we draw a large dot and a number with the number of water molecules associated with that compound. Many compounds exist as hydrates associated with water, tightly bound in specific ratios. We haven't dealt with hydrates yet, and we may not, but when you encounter them, that's what that means. Number 2, it says write the formula for each compound. Calcium acetate, so this is number 2. And A, calcium acetate, is cadmium acetate. I was looking at it. Cadmium is CD, and acetate is this, CH3COO-. So, depends on how you write it. I would write it that way, but I think they want us to write it C2H3O2. And this is a -1. Cadmium is +2. So to form this ionic compound, I need 2 of those. 2 -1s and 1 +2. The next one is what? Barium cyanide. So the cyanide anion, Cn-, sodium cyanide, the stuff that kills people. That is NaCN, because sodium and this Cn polyatomic anion has a -1 charge. So barium is +2, so I would have 2 of those. I put it in parentheses and put a 2 there. So my polyatomic ions, where these atoms all stay together, is set apart by parentheses, and the subscript indicates how many of them I have. The same way the subscript after each atom or element depicted tells you how many atoms of that element there are in the molecule. The next one is iron 3 phosphate. Phosphates -3. This iron, Roman numeral 3, is +3. So it's iron phosphate. You don't need parentheses. if you put them, it wouldn't make a difference. But it also says dihydrate. Dot 2H2O. So this has water associated with it. Manganese 2 nitrate. So this is that tricky one. This is not magnesium. It's manganese, Mn, not magnesium, the common group 2 metal Mg, magnesium. Mag wheels on your car have magnesium, strong but light, good metal. But it says manganese nitrate. Well, nitrate is NO3, but it's only -1. Okay? So I need 2 nitrates for the manganese 2. And then it says it's a hydrate, hexahydrate. So dot, big dot, 6H2O. That's only important in the solid. As soon as you put it into water and dissolve it, it goes away. And then finally, silver phosphate, which silver is +1. It's a transition metal, but only has one form, the +1. And phosphate is -3. So I need 3 silvers, 3 +1s to match that. Now I'm going to read the rest because that's where we're at. It says for part 4, write the empirical formula for the binary compound. Actually, let me go ahead and write those down so you can see them. I'll try and keep talking quickly and telling you, oops, I took 2 pages, oh well, no time to fix it now. The, let me get a red pen up. The rules for naming. We write the cation first and the other compound after. So this is number 4, and this is A, and it says zinc and sulfur. Sulfur is group 6. It forms a -2. Zinc always forms a +2. So +2 and -2, zinc and sulfur come together to form zinc sulfide. Barium and iodine, okay? Barium is what? Trying to remember where it is. I think it's +1, right? It's group 1 metal. And iodine is -1, like the halogens. Oh no, barium is a group 2 metal, so we need 2 I minuses, barium BaI2. Magnesium and chlorine. So, same thing, magnesium is a +2 because it's a group 2 metal, forms a +2 ion. If you look at the periodic table, you can tell that, and I'll discuss how to do that when we get to that point, but I'll show you a few tricks with some of the periodic tables we can use. They give you information about the valence or the charge on the most common ions. So, but chlorine is always -1, so it's MgCl2. For silicon and oxygen, you have silicon dioxide. This is in the same group as carbon. It forms 4 bonds. Oxygen's always -2, so it forms a -2 ion and combines in that ratio. Sodium and sulfur. Sulfur's always a -2 for our most obvious purposes. And sodium's always +1, so I would have Na2S in my sodium sulfide. For number 5, I have lithium and nitrogen. Nitrogen's, for most common purposes, is -3 for these purposes. So I need 3 + 1 lithiums for the -3 nitrogen. And so when it asked me to write the empirical formula, it would be Li, lithium 3, nitride. Cesium and chlorine. Cesium is group 1. It always forms a +1. Chlorine is group 7. It always forms a -1. So I would have cesium chloride. CaCl. It's Good, heavy, dense. This is a very heavy metal and forms some very dense solutions. Germanium and oxygen. Germanium takes two oxygens and forms germanium oxide like that. Rubidium and sulfur. Rubidium always forms a +1. Sulfur forms a -2, so I need 2. So when they're asking you to make up these formulas from the elements, they're trying to have you match the charges so that even though there's a -2 on the sulfur and a +1 on the rubidium, the overall compound has to have a net neutral charge, cannot have any charge. So the charges have to balance. That's what I'm doing. Arsenic and sodium. Arsenic's -3. Sodium is +1. So sodium arsenide would be Na3As. Now it says, write the empirical formula for each compound. This is your one quick exercise in empirical formulas, okay? It's the formula taken to the lowest common denominator. Na2S2O4. If I divide everything by 2, okay, then I get NaSO2. For B2H6, if I divide everything by 2, I get BH3, boron trihydride. For the next one, C6H12O6. That's the generic formula for hexosugars like glucose, mannose, galactose, fructose. And they have the general formula CH2O. This is where the term carbohydrate comes from, because they didn't know it was C6H12O6, but they did know they were in the ratio carbon to hydros. Not hydrogen, but water. Hydros from the Greek for water. Hydrogen means water generating, because when you burn it in oxygen, it generates water. So this is carbohydrate. Anyway, we'll move on. P4O10. Its empirical formula, its simplest formula is P2O5. And you don't get anything with this next one. It's potassium manganate, KMnO4. It's already in its simplest form. Okay? Now, it says complete the following table by filling in the formula for the ionic compounds for each thing formed. And it has chlorine, sulfate, phosphate, nitrate, and hydroxide. These are polyatomic ions. Okay? This is a subscript 4. This is a subscript 4. Sorry, I did not write them neatly. This is a subscript 3. I'll write them more neatly when we do them. And it says pair them with potassium, 1+, iron 3, 3+, ammonium ions, NH4+, and barium ions, 2+. Okay? So, our problem or our charge or assignment is to make the charges match. So potassium would form potassium chloride. Iron would form iron chloride with 3 chlorines, 1 of each. Ammonium chloride, very common laboratory chemical. Barium chloride, it's 2+, this is -1, so I need 2 chlorines to balance a charge and get to a neutral species when I put these ions together. This is what they're asking you to do. This assignment is, this question is, take the anions, the negatively charged ions, and mix them with these cations, positively charged ions. So in this problem number 7, potassium sulfate. And sulfate is 2 minus. This should have been a 2 minus. And phosphate is 3 minus. And nitrate is NO2. Sorry, NO3, that's nitrite. NO3, but it's -1 or 1 minus. The 1 is understood, okay? So, on the sulfate, it would be potassium sulfate is K2SO4. Here's your problem. Iron is 3 plus, sulfate is 2 minus. What do? I need to find a common factor, so I need 2 of these irons, Fe2. That gives me +6. And I need 3 of these -2s, SO4. Remember, you put it in parentheses, and I need 3 of those. Fe2, parenthetically, SO4, 3, iron sulfate. A very common ingredient, for example, in vitamins and iron supplements. You may have taken it. Ammonium sulfate, NH4 is 1 plus, so I need 2 of those to balance the 2 minus. And barium sulfate is BaSO4. For phosphate, I need K3PO4 for potassium phosphate. Okay, -3 plus 1, 3 of those. Here's a 3 and a 3, so that this iron 3, now iron can be either +2 or +3, but they told us iron 3 plus. I just need to do FePO4, iron phosphate. Okay, ammonium phosphate. I need 3 of these ammoniums because they're only +1 to balance out the 3 minus of the phosphate. And barium phosphate had the same problem we had before. I have a 2 plus and a 3 minus. I mean, before I had a 3 plus and a 2 minus, but I have that 2 and 3 factor. So I need 3 bariums to get to +6 and 2 phosphates. So I put in parentheses to get to -6 to balance it out and make barium phosphate. For the nitrate, I have potassium nitrate, KNO3, also known as saltpeter, also used in explosives and things. Iron nitrate, iron is +3, nitrate's -1. I'm going to need 3 of the nitrates, which individually are NO3 minus. The next one is ammonium nitrate, a wonderful fertilizer because it's got lots of nitrogen in it. 2 nitrogens, one in the ammonium and one in the nitrate. And barium nitrate, which would be Ba, which is 2 plus, and the nitrate's -1, so I need 2 of those nitrates. Now for the OH. This is hydroxide ion. It's what makes things basic. Okay, so for example, KOH along with sodium NaOH are known kind of collectively or interchangeably as Li. There's +1, -1. This is an insoluble compound, but iron hydroxide, yucky, gelatinous brown precipitate. Then ammonium hydroxide, common laboratory base, comes in a bottle with a green top, and barium hydroxide. The OH is -1, the barium is 2 plus, so I need 2 OHs there. And that's it for number 7. So it asked me to name compounds, and that's what I'm going to do in the next one. You'll just have to trust me. If you have any trouble, or you can't spell it, or you want to know more, Google it. Okay? Just put on this first one, Ni, nickel, O, oxygen. Just put NiO into Google, hit return, and it will give you information about it. Its molecular weight, its properties, what it's used for, and most importantly, in this case, its name. Nickel is a transition metal. It has more than one form or more than one possible charge. In this case, it's paired with oxygen, which is always -2. So this would be called nickel, parenthetically 2, oxide. For B, the next one is titanium. It's a transition metal. So it will be called titanium, parenthetically, Roman numeral 4, IV, dioxide. Titanium 4 dioxide. That's the way we say it. The next one has a trivial name that's in such common use, it's found acceptance in the scientific literature. This is known as nitrous oxide. You may know it as laughing gas. It's used as anesthesia in dentistry. It's used as a propellant in whipped cream. But its formal name is either dinitrogen oxide or dinitrogen monoxide. Usually you don't need the monoxide, but there's so many forms of these nitrogen-oxygen compounds that they tend to use it as they do for carbon monoxide. Okay, because there's carbon monoxide, carbon dioxide. This would be dinitrogen monoxide, but it also goes by nitrous oxide. The next one is carbon disulfide, carbon with 2 sulfurs. The next one is sulfur trioxide. The next one, NF3, is nitrogen trifluoride. And the last one is sulfur hexafluoride. Okay. And 5, 6, 7, 8. I seem to be missing a page. 1, 2, 3, 4, 5, 6, 7, 8. And I have another page. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. Nope, that's from the last one. Okay, 2.3. Here's my answer sheet. Well, I have another problem and it doesn't follow in my numbering system. So look around. Right now, I am talking about a question that says name each compound. And it has written there a number 5, A through F, and I will just rewrite them. A is HgCl2. This is mercury. This is the formula. This is the name. Roman numeral 2, chloride. Okay? I don't need to say dichloride because mercury 2 is always +2. And I know I need 2 chlorides because it's always -1. So I know I need 2 to balance out the +2 of the mercury. For B, it's iodine pentafluoride. IF5. And so it goes by the name iodine pentafluoride because FLUORIDE, the U comes first. In this compound, this is 2 nonmetals coming together. In fact, it's 2 halogens coming together. And it is a covalent compound that follows the covalent naming rules. In other words, you put the Greek prefix for the number of atoms present. The next one is one of those nitrogen-oxygen compounds. This one had an old trivial name of nitric anhydride, but it is now nitrogen, or you could, call it dinitrogen pentoxide. Dinitrogen. You didn't need to capitalize that nitrogen. And dinitrogen pentoxide. We don't say pentaoxide, but you certainly can. Everybody would understand what you say. But when you have 2 vowels in a row, we drop one. The rules get rather complex. Do your best. But when I'm talking later in the course and I say dinitrogen pentoxide, I need you to be able to visualize that and not, be totally lost about what that means. It means a nitrogen with an oxygen. The next one is Cl2O. So this Cl2O is chlorine dioxide. We don't say monochlorine dioxide because the mono is understood. And we name the first and then the second. In ionic compounds, like mercury 2 chloride, that cation comes first and the anion comes second. But this is a mixture of ionic and covalent compounds. This is practicing naming. The next one is Hg, that's mercury, S, sulfur, but the sulfide. So this is mercury. Sulfur is always -2, so this is mercury 2 sulfide. Sulfide. If you read a more international version of this, they will spell that with a PH instead of the F. They'll spell sulfide with a PH. And our last one that I know of, I'm sorry, I may have set a paper down, but I think I've gathered and worked through all of our problems, is PCl5. So PCl5 is phosphorus pentachloride. As in pentagon for 5. Phosphorus pentachloride. So I'm following our rules for naming covalent compounds and naming ionic compounds, working from putting them together to make sure the charges are neutral, taking the formula and giving the name, taking the name and writing the formula, taking the composition and putting them together to write the formula. It's just getting these chemical compounds named, written, so that we can all be on the same page when we actually start studying them and discussing them. So, this is the last part of chapter 2. I've started chapter 1 and gave you a balancing assignment. I will post the video help session for that a little bit later in the day. If not the day, then the next day. Like I say, it takes me many hours to upload these from my home internet. But if I get it done, that one is coming as well. The real quick short assignment on naming. And then I have 3 more assignments for chapter 3 that I'll be posting also at about the same time that I'm posting this. I can actually post those while this is uploading. Chapter 3, balancing equations, is next, using these compounds and thinking about these charges and everything. And so I'll show you why this is important in the context of studying chemical reactions, which is where we're going next. We have ionic compounds, covalent compounds, we have the formulas, we have their naming, and we're going to move into their formula weights and formula masses, and then we're going to start reacting them. So until then, keep studying, keep up, call me if you need me, especially text me, and I'll work through that email in the next day or so. I'm still behind. I've still got about 30 or 40 emails to answer, and I will see you in the next video. Goodbye now.